You've probably heard of gravitational waves. Who hasn't? I mean, they flooded our news channel this year. These tiny distortions in spacetime are so hard to detect that Einstein once asserted that humans would never be able to directly observe them. However, where there's a will, there's a way. On September 4, 2015, the LIGO detectors detected a merge between two gigantic black holes, releasing three solar masses of energy and gravitational waves. 3 months later, a second event was detected, with a third candidate under investigation. What are gravitational waves? Why are they so hard to detect? And how did we detect them? Well, objects with energy can create gravity. If it moves around, it can create gravitational waves, much like how an object moving in water creates water waves. Gravitational waves are transverse waves that look like this, or from a slice over here, like this. Gravitational waves were predicted in Einstein's general theory of relativity. Then why are they so hard to find? First of all, they're tiny. Two typical dashes spinning around in a circle would create a gravitational wave with amplitude 2 times 10 to the negative 50th at 1 meter away. That means that two objects 1 meter apart would move closer or further from one another by that tiny amount. Also, as you move away from the source, the signal gets sharply weaker. The amplitude is inversely proportional to the distance, so when you're 100 times farther, the wave is only 100th as strong. And gravitational waves interact only weakly with matter. They don't get absorbed or scattered like light. Then there's disturbance from the outside world. How do you know you really have a gravity wave, and not just someone stomping their feet next door? So, how do we do it? When gravitational waves pass through, they change the lengths between objects. We just have to measure this change to prove we have a wave. Problem is, the effects are tiny. Rulers can only measure to 10 to the negative 4th meters. So what do? We measure the difference between two different paths with light interference. If we have two runners running a close race, we let them run together and observe who comes to the finish line first. If there are two perpendicular tracks, when a gravitational wave passes through like this, or this, or this, it would stretch or compress at least one of them, and we just have to measure the difference. Since the light a LIGO uses has wavelengths on the scale of 10 to the negative 6 meters, we need that much change in our two tracks. Well, how big is the amplitude of gravitational waves from the spiring black holes by the time they get to Earth? 10 to the negative 21st. That's way smaller than 10 to the negative 6 meters, so we need to magnify the effect. First, we can use longer tracks. Of course, it is hard to tell the difference if two races run 1 meter. What about 4 kilometers? 10 to the negative 21st times 10 to the 3rd is 10 to the negative 18th. We're getting closer. Then we have the light bounce 100 times in the track, so it's 10 to the negative 16th. Then we can increase the amount of light, like 10 to the 20th photons. However, because of shot noise inconsistencies in the laser, this amplifies the effect only by 10 to the 10th, so 10 to the negative 16th becomes 10 to the negative 6. Finally! Not so fast though. There's another problem. There are random noises that can interfere with our measurements. To isolate the system, light is maintained in a near vacuum, and mirrors are suspended on pendulums suspended on suspension panels suspended on suspension panels, so that if the Earth moves, the mirrors don't. Scientists use patterns predicted in theory to filter and match results, and two observatories operate simultaneously, and only observations that match at both observatories in Livingston, Louisiana and Hanford, Washington can be considered a candidate. Having two stations also helps you tell from what direction the wave came using the difference in time it was measured at the two places. It wasn't easy. After finally convincing someone to fund the project, LIGO found nothing for 8 years. They closed the facility down for a 5-year upgrade using statistics from Germany, spending $620 million. Excitingly, after upgrading to advanced LIGO, they detected a wave even before officially operating the system. But they then had to examine and verify the statistics for months before releasing them, because confidence needs to exceed 99.99994% to prove the existence of gravitational waves. But they did it. P.S. Can you help in the search of gravitational waves? Yes! Einstein at Home is a massive computation project that uses ordinary computers to find gravity waves from spinning neutron stars. You just sign up online and they send calculations for a computer to do when you're not using it. Maybe your computer will be the one to find the next gravitational waves.